Okay, so welcome to Majorana-Raychaudhuri Seminar series again. So today's final speaker is Professor Robert Brandenberger from McGill University, and he's going to talk about emergent metric spacetime and early universe cosmology from the BFSS matrix model.
Okay, so first of all, thank you very much for the invitation to speak. And good early afternoon for those of you in Italy, good late afternoon for those of you in India, and good night for those of you in Japan. For me, it's early morning. So I'm going to talk about an approach to describe the early universe going beyond an effective field theory description. So, okay. So you all know that inflation is the current paradigm of early universe cosmology. And also, you know that inflation is usually analyzed using an effective field theory framework, general relativity, coupled to scalar matter fields. Now, I will argue that there are fundamental conceptual problems of an effective field theory description of any rapidly expanding universe. And the problems are a unitarity problem and an inconsistency with the second law of thermodynamics. So these are rather important problems. So if I manage to persuade you that there are indeed these problems, then the lesson that you have to take away is that we have to look beyond an effective field theory description if we want to understand the early universe. So now, matrix theory is an approach which goes beyond effective field theory. It is a matrix model, a quantum mechanical matrix model, no space. And specifically, I'll be looking at the BFSS matrix model, Banks, Fischler, Schenker, Susskind. And this is a matrix model which was proposed as a non-perturbative definition of superstring theory. So what I will do in this talk is I'll first discuss what I view as the conceptual problems of an effective field theory description of a rapidly expanding universe. In particular, these pose serious problems for inflation. Then I will remind you that there are alternatives to inflation if we want to explain the data that we now have. And then I'll go on and discuss the specific approach where we start with the quantum mechanical matrix model and we try to obtain an emergent space-time with a metric from it. And you will see at the end that we get a cosmology out of it. So this is the outline. So let me first discuss what I view as conceptual problems of an effective field theory description of a rapidly expanding universe. So here you see the space-time sketch of inflation. So the vertical axis is time, the horizontal axis is physical distance. And if you see my cursor, the time interval between T sub I and T sub R, that's the time period of inflation, preceded by something where there's an initial singularity. And after the end of inflation, you have the phase of usual standard Big Bang cosmology. So you're all familiar with this space-time diagram. And here I draw various length scales. First of all, there's the horizon, which is the forward light cone of a point at the initial Cauchy surface. So this is this line here. And during the phase of inflation, the horizon is expanding exponentially. Now, the second length scale, which I sketch here, is the Hubble radius, which is the inverse expansion rate. So during inflation, the inverse expansion rate is constant. Now, the red line is the physical wavelength of a fixed density perturbation. And during the phase where space expands exponentially, the wavelength of the perturbation expands exponentially as well. And so the success of inflation is based on the fact that scales that we see today on cosmological scales, for example, the scale that corresponds to the quadrupole of the microwave background, in the early universe, it emerges with a wavelength smaller than the Hubble radius, and therefore we can imagine moving matter around and creating density perturbations on this scale. Now, the last length scale which I plot is a Planck length. And I think you will all agree with me that effective field theory breaks down for wavelengths smaller than a Planck length. Now, as Jérôme Martin and myself pointed out more than 20 years ago, there's a trans-Planckian problem for inflation, namely the following. If inflation lasts only a little bit longer than it has to in order to explain the horizon problem, then scales that we observe now in the microwave background emerge at the beginning of inflation with a wavelength smaller than a Planck length. So obviously, if we really want to understand the evolution of fluctuations on this red wavelength, we need to go beyond effective field theory. Now, based on this trans-Planckian problem, a couple of years ago, Bedroya and Vafa postulated a new principle, which they called the trans-Planckian censorship conjecture, TCC. And the conjecture says that in no cosmology which is consistent with a quantum theory of gravity, modes which initially have a wavelength smaller than a Planck length can ever become larger than the Hubble horizon. So mathematically, this means that if we consider a usual Friedmann-Robertson-Walker metric with scale factor A of t, that if we start at any initial time t sub I with the Planck length and evolve to any later time t sub r, you have to remain smaller than the Hubble radius at this later time t sub r. So this is the trans-Planckian censorship conjecture. Now, I'm going to give you three justifications of this trans-Planckian censorship conjecture. The first is an analogy with Penrose's black hole cosmic censorship hypothesis. So here's a space-time sketch of a black hole with charge smaller than a mass. So there's a singularity at the center of the black hole, but an observer far away from the black hole is shielded from all of the bad stuff that happens at the singularity by a horizon. Now, general relativity, as an effective field theory, admits solutions with charge greater than the mass. And for those solutions, the observer far away from the center of the black hole is not shielded from the bad stuff that happens at the singularity. And so Penrose conjectured that the theory that completes general relativity must prohibit these pathological solutions where the observer far away from the black hole is not shielded from the singularity. So here's the Penrose's conjecture. The ultraviolet physics which completes general relativity must shield any external observer from the singularity and non-unitarity. And the shielding is by a horizon. Now, let's translate Penrose's conjecture from black hole physics to cosmology using this translation schema. So position space for black holes becomes momentum space for cosmology. The singularity for black holes becomes the set of trans-Planckian modes in cosmology. And I will replace the black hole horizon by the Hubble horizon. And so under this translation scheme, Penrose's cosmic censorship hypothesis says that an observer measuring only super-Hubble horizon modes must be shielded from trans-Planckian modes. And this is precisely the trans-Planckian censorship conjecture. So this is the first justification. Now, the second justification is a unitarity issue. So if you consider an effective field theory in an expanding universe, then inevitably the theory is non-unitary. So how do we see that? So if we take an effective field theory, then what do? We take all fields in the theory, we expand these fields in Fourier modes, and we quantize each Fourier mode like a harmonic oscillator. That's effective field theory, canonical quantization. No, in order to avoid the Planck catastrophe, we have to impose an ultraviolet cutoff. And this ultraviolet cutoff has to be at a fixed physical wavelength. And in an expanding universe, if you want to maintain the fixed physical ultraviolet cutoff, you have to continuously create modes. And this is non-unitarity. So now, if you demand that the classical region be insensitive to this non-unitarity, then you find precisely the statement that no modes, no Transplanckian modes can ever enter the classical region, namely enter the region where the wavelength is larger than the Hubble horizon. So this is a second justification of the Transplanckian censorship conjecture. And I want to make a side comment in this context. So if you use effective field theory, then you inevitably get the quantum aspect of the cosmological constant problem, because each harmonic oscillator has a ground state energy. You add up all these ground state energies, and then you get the cosmological constant. So I will now put forward the claim that the usual quantum view of the cosmological constant problem is an artifact of doing a wrong analysis. It's an artifact of doing an effective field theory analysis, which is inapplicable in a rapidly expanding universe. And I'll come back to this point at the very end of the talk, where I will show you that the new cosmology, which arises from this matrix model, has no quantum cosmological constant. Now, the third justification for the TCC is a thermodynamic argument. It is the statement that in a cosmology which violates the Transplanckian censorship conjecture, the second law of thermodynamics is violated. So those of you who work on black holes will know that there's been a lot of discussion between concerning the entanglement between stuff inside of the horizon and outside of the horizon. And similarly, there's entanglement between modes in cosmology which have a wavelength larger than the Hubble radius and those which have a wavelength smaller than the Hubble radius. So in a phase of inflationary expansion, you can compute the entanglement entropy density between sub and super Hubble modes. And here you see the reference. And you find that since the phase space of super Hubble modes is increasing, the entanglement entropy density is increasing. And if you demand that the entanglement entropy density remains smaller than the entropy density that we want at the beginning of the standard Big Bang phase, then we find that the duration of inflation is bounded from above, consistent with the Transplanckian censorship conjecture. So these are the three justifications for the Transplanckian censorship conjecture. Now, what does the Transplanckian censorship conjecture imply for inflation? And here's the space-time diagram for inflation, which you see again. So vertical axis time, horizontal axis physical spatial distance. The time interval between T sub I and T sub R is the period of inflation. Now, this curve here, which I'm lining out with my cursor, that's the Planck length. So in this sketch, I drew the Transplanckian censorship conjecture to be marginally satisfied. So the Planck length at the beginning of inflation grows to precisely the Hubble radius at the end of inflation. So the Transplanckian censorship conjecture sets an upper bound on the duration of inflation. But if we want inflation to be successful, then the wavelength that corresponds to our current Hubble horizon, T0 is the current time, we want to explain the origin of microwave anisotropies. So we need to make sure that the co-moving scale corresponding to the current Hubble horizon starts out inside of a Hubble horizon at the beginning of inflation. So this sets a lower bound on the duration of inflation, which I show to be marginally satisfied in this sketch. So the TCC sets an upper bound on the duration of inflation. Inflation being successful gives a lower bound on the duration of inflation. So are these bounds consistent with each other? This depends on where the Hubble horizon during inflation lies relative to the Planck length. The higher the energy scale of inflation, the closer the Hubble horizon is to the Planck length, and the more difficult it is to make these two criteria consistent. So let's do the math. The trans-Planckian censorship conjecture gives you an upper bound on the duration of inflation, which is characterized by this equation, demanding that scales that we observe today on cosmological scales at the beginning of inflation are smaller than the Hubble horizon at the beginning of inflation, gives you this lower bound on the duration of inflation. And you see that these two bounds are consistent, provided that the energy scale of inflation is smaller than about 10 to the 9 GeV, 5 orders of magnitude lower than it is in simple models of inflation. And if you have such inflation with such an energy scale, then the primordial gravitational waves are utterly negligible. So inflationary models, which are consistent with the trans-Planckian censorship conjecture, predict a tensor to scalar ratio, which is utterly negligible. So please never accept anyone who tells you that B-mode polarization is a smoking gun of inflation. It is absolutely not true. In alternatives to inflation, typically you get a larger tensor to scalar ratio than in inflation. Okay. So the trans-Planckian censorship conjecture also has implications for dark energy. Dark energy cannot be a bare cosmological constant, and even quintessence models are constrained. Okay. So hopefully I've persuaded you that there are severe conceptual problems of inflation if you treat inflation using effective field theory. Okay. Now, I will briefly remind you that we don't need inflation to explain the current data. There are good alternatives. So we want to explain the current data, for example, the anisotropies in the cosmic microwave background. So here you see amplitude of anisotropies of the cosmic microwave background, vertical axis, versus angular scale, horizontal axis. The black dots are the data points from WMAP with statistical errors, systematic uncertainties. And the red curve is an artist's curve which fits the data fairly well. And what physics do you need in order to get the red curve? And the answer to that was well understood 10 years before the development of inflation. There are two beautiful papers, one by Zeldovich and Zuniaev, and the other by Peebles and Yu in approximately 1970. And they laid out the conditions which a early universe cosmology has to obey if you want to explain this data. And here's a reproduction of a graph in the Zeldovich-Zuniaev paper. Vertical axis is time, horizontal axis is co-moving distance, and this diagonal line, or this time here, that's a time of recombination when the microwave background is released. The diagonal line is the Hubble radius during the period before recombination. So Zeldovich and Zuniaev argued in the following way. Assume that there is a mechanism that produces fluctuations on all scales initially. So on scales larger than the Hubble radius, fluctuations are standing waves. They don't oscillate. Fluctuations only start to oscillate once the wavelength becomes smaller than the Hubble radius. So as you see in this sketch, the fluctuation mode which enters right at recombination, it has not had time to oscillate at all. So we catch this mode at maximal amplitude. This mode has had a time to do 5/4 of an oscillation, and therefore we catch this mode at minimal amplitude, maximal velocity, and so on. So you see that this oscillatory pattern in the number of oscillation times of the mode precisely explains these acoustic oscillations in the angular power spectrum of the microwave background. So the origin of these acoustic oscillations in the angular power spectrum of the microwave background was well understood 10 years before inflation. And in no way it is a prediction of inflation. So this is the summary in words of what I just said. Given a scale-invariant power spectrum of fluctuations initially on all scales, and this kind of power spectrum was known to be good for explaining the distribution of galaxies. And if you have such fluctuations, then you predict acoustic oscillations in the CMB angular power spectrum, and you predict baryon acoustic oscillations in the matter power spectrum. So in order to realize, the key question which was not addressed by Peebles and you and Zuniaev and Zeldovich was the origin of these initial fluctuations. Okay. So, good. What are the criteria for a successful early universe scenario? So first of all, the current, the horizon has to be much, much bigger than the Hubble radius. Otherwise, we can't explain the isotropy of the microwave background. So secondly, scales that we observe today have to originate inside the Hubble radius at early times. Otherwise, we have no mechanism to produce these fluctuations which were postulated in 1970. And finally, the mechanism which produces these fluctuations must produce them with a scale-invariant spectrum. So these are the three criteria for a successful early universe cosmology. And in inflation, these three criteria are realized. This is the space-time sketch of inflation again. So you see that in inflation, the horizon is exponentially larger than the Hubble radius. Fluctuations which we observe today start out in the early universe with a wavelength smaller than the Hubble radius. So that first two criteria are explained. And the fact that we get a scale-invariant spectrum of fluctuations is related to asymmetry. It's related to the fact that the energy density during inflation is constant. But another way to realize these three criteria is a bouncing cosmology. So here's a space-time sketch of a bouncing cosmology. So in a bouncing cosmology, we assume that the scale factor of the universe starts out contracting, and then there's some new physics beyond effective field theory, which gives you a transition between contraction and expansion. And this gives rise to this space-time diagram. So time, co-moving spatial coordinate, and these diagonal lines, it's a Hubble radius, and these vertical lines, they indicate wavelengths of perturbations. So in a bouncing cosmology, the horizon is infinite. Time runs from minus infinity to plus infinity. As you see here in this sketch, fluctuations start out inside of the Hubble radius at sufficiently early times. Criterion 2 satisfied. Now, like in an expanding universe, there is a subclass of contracting models where initial vacuum fluctuations evolve into scale-invariant fluctuations just before the bounce. So like in an expanding cosmology, not all expanding cosmologies give scale-invariant spectra of perturbations. In bouncing cosmologies, not all bouncing cosmologies give rise to scale-invariant spectra of fluctuations, but there are certain classes of bouncing cosmologies where you can get scale-invariant fluctuations. But I'm not going to talk about bouncing cosmologies here. I'm going to present you a model of an emergent universe. And from the point of view of the evolution of the scale factor, A of t, an emergent cosmology is a cosmology where there's an initial phase where the scale factor is constant, and then there's a phase transition to a phase of standard Big Bang-like expansion. So this is the hypothesis that underlies an emergent universe. This is the resulting space-time diagram. So time is the vertical axis, space is the horizontal axis. This is the emergent phase. This is a standard Big Bang phase of expansion. The horizon is infinite. The blue curve indicates the Hubble radius, which is also infinite in the static limit. And the red lines, they give rise to the wavelength. They are the wavelengths of fluctuations. In the static phase, the wavelength is constant. So you see, horizon is infinite. Fluctuations emerge with a wavelength smaller than the Hubble radius. So the first two criteria are satisfied. And the statement now is the following. If you start in the emergent phase with thermal fluctuations, with holographic scaling, then that induces scale-invariant spectra of cosmological perturbations and gravitational waves. So what I try to show you very briefly here is that there is more than one early universe scenario which is consistent with data. Now, in order to get a bounce in cosmology, you obviously have to go beyond an effective field theory description, because otherwise you will not get a bounce. If you want to obtain an emergent cosmology, then you also have to go beyond the effective field theory of general relativity coupled to classical matter. Because if you just use Einstein gravity, classical matter, you will never get a static phase with lots of energy. So now I argued in the first part of the talk that if you want to describe inflation in a consistent way, you also have to go beyond an effective field theory description. So all early universe scenarios require going beyond an effective field theory. So let's try to go beyond an effective field theory. Okay, good. So you're probably not familiar with emergent cosmologies. So let me give you a toy model of an emergent cosmology, and this is string gas cosmology, which Cumrun Vafa and myself developed in 1989. So string gas cosmology is based on replacing point particles by fundamental strings. So instead of taking a space-time filled with point particles, let's take a space-time filled with fundamental strings. And let's look at the new degrees of freedom that distinguish strings from point particles. And these new degrees of freedom that strings have and point particles don't have are oscillatory modes of strings and winding modes of strings. So if you take a gas of closed strings, then in thermal equilibrium, there's a maximal temperature. For gas of point particles, there is no maximal temperature. Now, if space is compact, then point particles can whiz around this space, but they cannot wind the space, whereas strings can wind the space. So the string oscillatory modes and the string winding modes are features which distinguish string theory from point particle theories. So let's look at the implications of these new degrees of freedom. So associated with the momentum and winding modes is a new symmetry which says that physics on small scales is equivalent to physics on large scales. So the energy of center of mass motion modes is quantized in units of 1 over r, where r is the radius of the spatial torus, whereas the energy in the winding modes is quantized in units of r. So if you place r by 1 over r and you interchange momentum and winding quantum numbers, then the mass spectrum of string states is unchanged. This is also a symmetry of non-perturbative string theory, and this is a key difference between point particle theories and string theories. So let's do adiabatic considerations. Let's take a box of strings with radius r in thermal equilibrium, and let's follow the temperature of this box of strings as you reduce the radius of the box. Now, initially, when the box is very large, the energy will be in the degrees of freedom which are light when the box is large, namely the momentum modes. Now, as you shrink the box size, the momentum modes become heavier, and eventually the energy density becomes so large that you can start to produce these string oscillatory modes. The level of increase in the temperature will level off. You will never exceed the maximal temperature, the Hagedorn temperature. And once the radius becomes smaller than 1 in string units, the energy can flow into the winding modes, which are light, and the temperature will decrease. So this is the thermodynamics of a box of strings. There's no temperature divergence. Now, based on these adiabatic considerations, Vafa and myself postulated that the cosmology that arises from this will have a phase, quasi-static phase, where the universe loiters at a temperature close to the Hagedorn temperature. So we postulated that we will get this cosmology. The scale factor will start out to be constant in this early phase where you have a gas of strings close to the Hagedorn temperature. And then there's a phase transition where the winding modes can decay, because it's the winding modes that prevent space from expanding. Now, this process of winding modes decaying can only liberate 3 dimensions of space. So in this setup, you start with a 9-dimensional space. The string theory is only consistent in 9 spatial dimensions. But this phase transition will liberate precisely 3 dimensions of space. 3 dimensions of space become large. The other 6 dimensions are forever wound by strings. This is this. So we have this SO9 to SO6 cross SO3 symmetry breaking. And I'll come back to that at the end of the talk. Okay. So we get this space-time diagram, the emergent Hagedorn phase, the standard Big Bang phase of expansion. We have a thermal gas of strings. We can compute thermal fluctuations of the strings, and we can compute the induced curvature perturbations and gravitational waves and compare with observations. Okay, so the way we do these calculations is the following. We compute the matter correlation functions in this early phase. Wavelength by wavelength, we convert the matter fluctuations to metric fluctuations. And then we evolve the metric fluctuations through the standard Big Bang cosmology phase. All we need to do these calculations is the partition function of the gas of strings. Okay, so this is how we do the calculations. We want to compute curvature perturbations and gravitational waves about the homogeneous and isotropic cosmology. So everything in blue is homogeneous and isotropic background, and the red are the space and time-dependent fluctuations. Now, the curvature perturbations are given by the energy density perturbations. The gravitational waves are given by the off-diagonal pressure perturbations. We have the partition function of a string gas. We can compute these quantities here. We can compute the induced curvature perturbations and gravitational waves. This is how we do the calculations. The energy density perturbations are given by the specific heat capacity. Specific heat capacity is given in this way, holographic scaling. We can compute the power spectrum of cosmological perturbations. It turns out to be scale-invariant with a slight red tilt. We go on and compute the gravitational waves. They are scale-invariant, but with a slight blue tilt, unlike for inflation. So you see, we don't only have an alternative to inflation, but we have an alternative to inflation which makes predictions with which it can be distinguished from inflation, which is his last line. So I went very quickly through these past few slides. So this is just a toy model of an emergent cosmology. And the Achilles heel of this toy model is that we just put in this cosmological background by hand. We had no dynamics for this early phase. And this is what we are now going to obtain from this matrix model. So now I'm more than halfway through the talk, so don't worry if you're looking at the clock. So I will now try to show you how we can take a non-perturbative definition of superstring theory, which has no space, and we can get out of this model, we can get a metric space-time and an early universe cosmology, which realizes string gas cosmology. Okay, so the starting point of our analysis is the matrix model, which was proposed back in 1996 as a non-perturbative definition of superstring theory. So it is a quantum mechanical model of 10 n by n Hermitian matrices There's no space, therefore no singularities. And we want to take n, the size of the matrix, to infinity. This is the Lagrangian. So there's a term here which looks like a kinetic term. There's a term which looks like a potential term. There's a coupling constant. And this dt is partial derivative with respect to time plus commutator with respect to a matrix A sub 0. So it's a well-defined matrix model without any kind of singularities, without any space. Now, what we do is we consider this matrix model to be not in the vacuum state, but in a high temperature state. So in this case, we can expand all matrices in Matsubara modes. We can expand them in the complex time direction. And we choose our temperature to be so large that the action that you get by inserting this expansion into the action is dominated by the small n equal to 0 modes, by the modes which are independent of Euclidean time. So the idea is that it is these n equals 0 modes which are going to give us the background space, and the n not equal to 0 modes, they are going to give us the thermal fluctuations which live on the background. Now it turns out, since I think there are people in Japan who are online, that the action, the part of the action that describes the small n equals to 0 modes, this is the IKKT action, which is the pure matrix model action, which was proposed by these authors as a non-perturbative definition of type 2b superstring theory. So this is the action that describes the mi-0 modes. This is the partition function. So we have a partition function, and therefore we can compute partial derivatives of the partition function. We can compute fluctuations. Okay, so this is the model that we take. No singularities, no space. Since we pick a finite temperature state, there's no more evolution. We've lost time. No space, no time, but no singularities. And now we have to, from this starting point, we have to obtain time, we have to obtain space, we have to obtain a metric, and we have to obtain an early universe cosmology, and all within 5 minutes. Okay, so these are Hermitian matrices, so we can diagonalize one of them. And we will diagonalize the A sub 0. And the eigenvalues of this A sub 0, those are going to be the instances of time. So this is how we obtain time, the eigenvalues of the temporal matrix A sub 0, that is time. And in the limit where n goes to infinity, the size of the matrix, you can show that the distance between temporal eigenvalues goes to 0, and the extent of time goes to infinity. And it goes to infinity both in positive and negative time direction. So this matrix model is giving us an emergent time which runs from minus infinity to plus infinity and is continuous. So this is time. So now let's move on to space. So we continue to work in a basis in which A naught is diagonal. The spatial matrices are not diagonal, but you can show that they have these properties. So if you look at the spatial matrices and you go away from the diagonal and you look at the expectation value of these spatial matrices, as you increase the distance from the diagonal, then you find that when you get to a distance greater than this n sub c, where n sub c scales are square root of capital N, then these objects decay away. When you are smaller than n sub c, you're approximately constant. These two first properties you can show using the Riemann-Lebesgue lemma. You need numerical work done by Nishimura and his collaborators to show the last point. So now we want to make use of these properties of the spatial matrices to obtain space. So what we do is the following. We work in a basis in which the temporal matrix is diagonal, and we look at the spatial matrices. And we want to define space at a particular value of time. So let's take this time here. So in order to define space at this time here, we take the spatial matrices, we go down a distance t along the diagonal, and we look at subblocks of the spatial matrices of small size n sub I, where n sub I is smaller than this n sub c here. Okay, and now we can consider these quantities, expectation value of the trace of these submatrices. And Nishimura and collaborators, they've called this the extent of space parameters. And they have observed using numerical simulations that there is spontaneous symmetry breaking, that as time increases, only 3 of these extent of space parameters become large, the other 6 remain small. The same phase transition that happens in string gas cosmology. And it is the same reason which explains this phase transition. Okay, so let's be just a little bit more precise. What our proposal is to view the size of the submatrices n sub I. We view these as our co-moving spatial coordinates. And this quantity here, the extent of space parameter, that is the physical length of a curve between n sub I equals 0 and n sub I. So we have our co-moving coordinates. We have a length, so we have space. And if we have co-moving coordinates, we have a length. We can compute the metric using the usual way you do it in general relativity. And if you use the properties of these matrix elements, you can show that the spatial metric component GII, which you get using this first equation, that they are independent of space. So the metric that emerges, the spatial metric that emerges, is spatially flat. Good. So this is our prescription of obtaining infinite continuous time, infinite continuous space, a spatial metric which is spatially flat, all from this matrix model which was proposed as a non-perturbative definition of superstring theory. Okay, the final point, which is very brief, the cosmology. So first of all, in the subspace of the 3 spatial dimensions that become large, we can solve the classical equations at late times, and we can find the time evolution of a scale factor, and you find that it looks like a radiation-dominated universe. There's no sign of a cosmological constant. We never quantize any harmonic oscillators, so why should there be a cosmological constant? So this reinforces the conjecture I made at the beginning of the talk, that the usual quantum view of the cosmological constant problem is an artifact of using effective field theory in a context where it cannot be applied. Okay, now we have all the small n not equal to 0 modes. We are starting with a thermal state, so therefore we have thermal fluctuations. We can compute the thermal correlation functions like we did for string gas cosmology. And what we get, so again, these are the equations that you've already saw in string gas cosmology. We have the partition function of the matrix model. We can compute these correlation functions. This gives us the curvature perturbations and gravitational waves. And you won't be surprised that the answers are exactly like in string gas cosmology. We get scale-invariant spectra of curvature perturbations and gravitational waves. And the curvature perturbations actually have a Poisson contribution on ultraviolet scales. The gravitational waves do not. So I'm essentially finished. In the last part of the talk, I've tried to show you an approach where we start with a matrix model, which is a non-perturbative definition of superstring theory. And we've given you a prescription to get emergent infinite space, emergent infinite time, an emergent metric, which turns out to be spatially flat. and an emergent early universe phase with thermal fluctuations leading to scale-invariant curvature perturbations and gravitational waves. So everything that you really would like. Now, obviously, there are lots of open problems. We have not included the fermionic sector of the matrix model. We do not understand the phase transition sufficiently well. We haven't shown that we actually get general relativity in the low energy limit. I know how to approach this problem, but we haven't written it up yet. And at the very end of the research program, we also have to address the origin of dark energy. So there are lots of open problems. We're just at the start of this ambitious research program. So let me try to conclude. I have two concluding slides. One is robust conclusions that I would like all of you to be persuaded of. So inflation is not the only scenario of early universe cosmology which is consistent with current data. And in light of the Transplanckian censorship conjecture and other conceptual problems, effective field theory models of inflation are not viable. This doesn't mean that inflation is not possible, but if we want inflation, we have to go beyond effective field theory. So, in light of the Transplanckian censorship conjecture and other conceptual problems, dark energy cannot be a cosmological constant. Dark energy is something very, very mysterious. It's going to teach us a lot. It is not a cosmological constant. And we know that from conceptual problems. We definitely need to go beyond an effective field theory description if you want to describe the very early universe. So these are what I view as robust conclusions of my talk. Now, the second concluding slide is basically a summary of our approach to go beyond an effective field theory. So what we do is we start with a matrix model, which was proposed as a non-perturbative definition of superstring theory. We consider this model in a high temperature state, and we gave a prescription to get emergent space, time, and metric. The emergent space is spatially flat and infinite. We have thermal fluctuations, and the thermal fluctuations can explain the cosmological fluctuations that we've observed. And these thermal fluctuations make predictions for gravitational waves. And the prediction is scale-invariant spectra with a slight, very slight blue tilt, with a consistency relation, which I could mention. So let me go back to the robust concluding slide, and I thank you for your attention.